In this video, we will see 3 examples of using the Wronskian of functions to determine linear dependence of the functions. Example 1. We need to check whether or not these 2 functions are linearly dependent. So we can use the Wronskian to solve this problem. So first of all, we need to find the Wronskian of the 2 functions. And this is the definition, right, which is the determinant of the matrix consisting of the 2 functions and their derivatives. So now we just put the 2 functions into the first row. And then for the derivatives, the first entry's derivative is pretty straightforward. It's just e to the x, right? But for the second function, we have to use the product rule. Okay, so for e to the x, its derivative is just e to the x, and then times the second factor, which is sine x. And then you have to do e to the x times the derivative of sine, which is cosine x. And then you factor the e to the x out. So that will be the derivative for the second function. Okay, now we need to carry out the determinant of this matrix. And we understand for a 2x2 matrix, its determinant can be obtained from the product of the diagonal entries minus the product of these 2 off-diagonal entries. Okay, so we just carry them out. So you can see the product of these 2 entries minus the product of these 2 entries. You're going to get e to the x times e to the x is going to be e to the second x. And that's a common factor. So you got this out. And then the first term will give you sine x plus cosine x. The second term will give us minus sine x. So after the cancellation, you're going to get e to the x times cosine x. And we know this is not going to be equivalent to 0. For example, when you check the expression for x is equal to 0, you're going to get this is 1, and this is another 1, right? So the product is going to be 1, which is not always 0, right? So therefore, we understand these 2 functions are going to be linearly independent because their Wronskian is not equivalent to 0. Example 2. We need to check whether or not these 2 functions are linearly dependent. So again, we need to first of all carry out the Wronskian. So we're going to put the 2 functions in the first row and their first derivatives in the second row. For both of these, you're going to say you have a product, right, for both entries. So I have to use the product rule. And for the first function, you're going to say the derivative for x is going to be 1, right, and then times e to the x. And then you have to check out the derivative of e to the x, which is going to be itself, right? So you're going to get x times e to the x for the second term. And then you factor the e to the x out. This will be the second derivative. And for the second entry, the derivative for x is going to be 1, right? So you're going to get 1 times e to the negative x. And then the derivative for e to the negative x is going to be minus e to the negative x times x, right? So you're going to get minus x times e to the negative x. Okay, now for this 2x2 matrix, the determinant is again the product of the diagonal entries minus the product of these 2 off-diagonal entries, right? So you just carry out the multiplications. And in this case, you can say the e to the x times e to the negative x. This product is going to be 1, right? So therefore, the first term will give us x times 1 minus x, which is x minus x squared. And the second term is actually x times 1 plus x, right? And you have a negative sign here. So it's going to be minus x squared. So after cancellation, we're going to get this is equal to negative 2x squared. And apparently, this is not going to be equivalent to 0. So because the Wronskian is not always equal to 0, we know these 2 functions are linearly independent. Example 3. This time we have 3 functions, and we need to use Wronskian to check the linear dependence of the 3 functions. The Wronskian actually is defined in a similar way, okay? But because you have a dimension 3, right? So you have to get a new row of a higher derivative. So namely, you can say the functions in the first row, first derivatives in the second row, and the second derivatives in the third row, so that we can have a square matrix here. We have polynomials for these functions, right? So the derivatives are pretty straightforward. So you can say these are the functions, and the derivative for the first, you can say it's going to be 2, right? And the second derivative for this, for constant, is going to be 0, right? For the second function, the derivative for this is going to be 2x plus 1, and the second derivative is going to be 2. For the last function, you can say the first derivative is going to be 4x, right? The constant is going to give you a 0. And then the second derivative is going to be 4. Okay. For 3 by 3 matrix, you can find it's determined by expanding, according to either a row or a column, right, of the matrix. So that's a standard approach. But we do have a shortcut, right? So namely, we can put the first column here and the second column here, right? And then we're going to have some diagonal directions. So I have 3 of them, right? And the kind of backward direction, we also have 3 of them, okay? So then we're going to have some formula similar to the formula for the 2 by 2 determinants, okay? So for these diagonal directions, you're going to get positive sign assigned to the products of them. And for the inverse direction, you're going to give a negative sign to the product of them, okay? So namely, you can see here, for the first 3, we get a product and we have a positive sign, which we don't usually put it there, right? And for the second 3, we have the products here and we have a plus sign. And then we have the last 3 in the diagonal entry, right? Diagonal direction, we have a plus sign. And for this inverse direction, we have a negative sign in front of them, right? So you have the product here for the first 3, and the product of the second 3, and the product of the last 3, right? And now we just need to carry out this is essentially a polynomial, right? We just need to carry out the multiplications and get the polynomial, okay? So I'm going to copy this expression, okay? And then we need to work on this. Well, of course, you can just carry out the product, okay, for each term, right? So that's one thing you can do. And here, actually, we can also think about, for example, doing common factors, okay? For example, first of all, you can say these 2 terms, because you have a 0 factor, right? So they are going to be 0, right? So we don't have to think about these. And for the remaining 4 terms, you can use a common factor thing, okay? For example, you notice that for this term and this term, you have the 2x plus 3, right? So we can factor this common factor. And the first term, you can say it will give us 8x plus 4, right? And for this term, you're going to get an 8x. So we can combine these 2, okay? And then for the other 2 terms, you can see here, we got 2 times 2 is going to be 4 times of the 2x squared minus 3, right? And for the last one, you're going to get 2 times 8, which is 2 times 4, which is 8 times of x squared plus x, right? So now we can just carry out these products easily, okay? In particular, for this first one, the 8x cancel the 8x, you're going to get 4 times of the 2x plus 3, which is going to be 8x plus 12, right? The second term, you're going to get 4 times of this, which is 8x squared minus 12. And the last one, you're going to get minus a squared minus 8x. And now you can see the x squared terms canceled out. The x terms canceled out, right? And the constant canceled out. So this is going to be equal to 0 no matter what x. So that means the determinant is going to be equivalent to 0. And in this case, we understand the 3 functions, they are linearly dependent, okay? Because we know if the determinant, namely the Wronskian, is equivalent to 0, then we know the 3 functions are going to be linearly dependent, okay? So that's why we can draw this conclusion. Okay, so that's all for this video, and thank you for watching.